So hello everyone, my name is Dmitry. I came from Lithuania, from Vilnius. I'm really happy to be in Warsaw. It's my first time and I enjoy the city. I had like one day before and today. And thanks for organizers for having me here. Uh, I work in Lithuania as a backend engineer at Vinted. In Vinted, we aim to make secondhand the first choice worldwide. We are the world's biggest fashion marketplace, working in 12 countries, having 11 millions of members. We also work in Poland. If you haven't tried it, you can check it out. And today I'm going to tell you about an idea of creating a new application server for Ruby and MRI, the fastest application server. But before continuing, I would like to pay some attention to this slide. As I believe most of you know what it is, it's a new relic timing for our request response cycle of our Ruby application. So when our applications grow and when performance start to matter for us, we look at this graph trying to figure out where to save some milliseconds or sometimes even seconds for this request response cycle. We aim to make user experience better, or we try to save some resources and therefore costs for our infrastructure if we can reduce some time here. We are searching for some bottlenecks in our own code, in our database queries. We try to use the most efficient gems and software for our apps. And in Ruby, which is itself the language with not the highest performance, so you can see the blue area on this graph, it stands for Ruby. And there always is a room for improvement. And application servers, as they are Ruby apps, they are included to this big blue area. To recall where app server stands in our typical Rails stack, we can see that requests come to first to web server, which is typically Nginx or Apache, then it goes to application server, and then through middleware and controllers to our business logic, and it goes all the way back the same. So app server is an entry point of every Ruby web app, meaning that requests from our clients hit Ruby world in app server. They do a really heavy job for parsing HTTP requests, extracting headers, extracting many information from there. And as you may know, the most popular servers for now are Unicorn, Passenger, and Puma. I heard that actually the most popular one is WebRig, but since Rails 5 has Puma by default, it soon, I believe, become not true. And here I would like to know that I really love systems programming, low-level programming. I love languages like C and C++. You feel much more freedom comparing when you are developing in Ruby. But when your C or C++ apps grow, you need to keep in mind so many things, especially related to memory management, to threading, to concurrency. If you miss something, your applications start to crash, to segfault. And at that time, I already had experience with Rust language. So I decided to try it for this project. Rust is a language which is featuring zero-cost abstractions, smooth semantics, guaranteed memory safety, and so on, but I personally think about Rust just as a better C, meaning that it's as low-level language as C, but you don't have to worry about memory management, about concurrency. Basically, it means that if your Rust program compiles, it will not crash. Otherwise, it's compiler bug in Rust itself. So if you like low-level programming, you can try Rust. This company has already tried it and they use it in production. So coming back to the server. Sorry, can you see the slides on that side? Yeah, thanks. I had fast Rust language on one side and slow Ruby language on another side. So what can be done here for app server to speed it up? It may be just okay. Let's try what we can do here. Yeah, it's sec fault, like a blue screen of death. Yeah, great, thank you. So fast Rust on one side and slow Ruby on another side. And to make app server faster, we can just try to extract the most heavy job from Ruby world to Rust world. For example, listening on TCP or Unix socket for new requests, parsing them, prepare for Ruby, and then pass to our rack app, let's say to Rails. But to do that, there is a need for some way for communication between Rust and Ruby. The first choice may be FFI, but it really didn't work here because, first of all, FFI is unidirectional, meaning that you can call some Rust code from Ruby and return some result. But if you want to make it work another way, for example, we receive request on the Rust side and we want to pass it to Ruby. So FFI doesn't allow it. And also another thing about FFI, that if you want to work with some complex object, I mean something more advanced than arrays, let's say hashes or structures, it may be a request structure which has URI, query string, set of headers. FFI requires to have a bit complicated code and passing pointers, manually allocating memories, and that is why we use Rust, to not have any row pointers or any allocating memory ourselves, because it makes application unsafe. And there is another way, it's native extensions. I believe even if you haven't written native extensions yourself, you saw like bundle install, failed to build native extension, something. This native extension, they allow to have a protocol which is not unidirectional. Moreover, it allows to attach some Rust or C library to your running Ruby application and define a new class in Ruby app, define new module, instantiate objects. Also, they allow to replace some already existing code in Ruby. For example, if you have some instance method of some class which is really slow, which does heavy computation, you can replace that method with Rust or C code. It will still have the same interface, just instance method of some class, but under the hood, it will be a fast Rust code, not the Ruby code. For example, these gems use native extensions. They do really heavy job, like accessing database, accessing cache, parsing JSON. These are the things which our apps do hundreds or thousands of times per second. And we don't want to pay any additional cost or any additional time for those operations. So what is native extension under the hood? MRI provides a set of functions and set of external constants which can be accessed from C or Rust code. And by calling these functions, you can do some work, some interaction with your running Ruby program. For example, RB define class with some given name as a string will define a new class. RB define method obviously will define some new method. Array pop element from the given array to this RB array pop function, hash size or string length. And after some experiments with native extensions, I saw that this way it may work. It may allow to create the application server. But first, I decided to create some intermediate level, a library for interaction between Rust and Ruby. Not just having a set of thousands of C functions and constants, but create some nicer API, because we all as Rubyists will have good-looking code, well-defined DSLs, and not just having thousands of functions which you just call and pass some parameters between them. The tool was called Ruru. It's basically Rust plus Ruby or Ruby plus Rust. The first commit was made in October 2015, and after about half a year, in April 2016, it was open sourced. It reached some state where it could be already used by other developers. You can find the code on GitHub. Also, we have a weekly blog. Some examples. Yeah, actually there was a funny situation. There was a Ruby conference in Lithuania. Piotr was speaking there. It was like 2 or 3 days after the release of Ruru, and Steve Klabnik gave a talk there about Rust for Rubyists, and he showed some slides about Rust, and he said like, oh, I will show how to use Rust with Ruby. And he opened, oh, this is Ruru, and I was sitting there in that conference like, I just released it 3 days ago, and he will show some demo, and it didn't compile, something didn't work. We fixed that after the conference, so it was some part of the history of Ruru. So about examples, for example, if we want to define some simple Ruby class, empty class user, how it can be done with Ruru? It's class new user. None here stands for no explicit superclass, no class to inherit from. The same user class with attribute reader, class method, and instance method will look like that. The beginning is the same, new class user, and then we define the body of that class. So attribute reader age, class method create, and instance method email valid. Next, we don't use it often in our daily work. We create a new instance of array, and then we modify its singleton class of that array instance. It should look like this in Ruby, the same new instance of empty array, and then we take singleton class and define attribute reader on that, and check if current array instance responds to the new method. And also the new upcoming version of Ruru will support rescuing exceptions. Should look pretty similar, like begin block, argument error, rescuing, type error, and all other kinds of errors. And about benchmarks, how native extensions compare to plain Ruby code, I took a project, it's priority queue. Priority queue is basically just a simple plain queue where you push some object, but when you want to pop objects from the queue, they can be prioritized. You can give some block, a Ruby block, which will say in which order to pop the objects from the queue. For example, if you have a queue of bugs in the application, you may say that first I want to pop critical bugs, then high priority bug, then low priority, and then whatever is left there. And it was compared to algorithm gems, which is gem which provides algorithm in Ruby. For benchmarks, it was used pushing 50,000 of elements and popping 50,000 of elements from the same queue. As you see, pushing is itself much faster. Popping is a bit faster. So you can check it out. There are more examples in GitHub, in documentation, and coming back to the server. So there was a way for communication between Rust and Ruby, this Ruru, and I could try to implement the basic version of the server itself. Also, here I will show you some dark corners of MRI, those things which we don't usually face in our daily work, but they still exist in MRI. And I believe if one day you will face those issues, this may be helpful for you. The base version of the server may be single-threaded mode, similar to one instance of Unicorn or one instance of Puma or Passenger in having one thread. As a backend for a server, Hyper was chosen. Hyper is a fast, multi-threaded HTTP server written in Rust and for Rust. It's not a web framework with routers or controllers. It's just a lightweight abstraction over HTTP. Hyper has a concept of handlers. In the simplest case, handler may be just a function which gets a request and returns some response. It can be attached to a TCP or Unix socket, and what happens when you launch Hyper server? Hyper spawns several native threads, which each of them is listening on the socket which is given to the server, and each of the threads run an instance of a handler. So the requests can be processed in parallel. And how can it be connected to our Ruby apps, to Rails? How this can become the application server for Ruby? It may be something like this. So we point our handlers to Rails application, use Ruru in handlers, just get Rust requests in handler, process them to make a Ruby request like rec compatible hash and pass to Rails. And maybe here you may have a question like, if we run Rails application in single-threaded mode, why multiple native threads should be used here for handlers? The question may be the answer may be here that Rails is slow, right? And it may take some time to finish processing one request on the Rails side. So at that time, while Rails is doing its job on one request, other handlers in parallel may receive more requests from socket and do some preparation. Parse headers, parse body, create rec hash, and as soon as Rails becomes free, the prepared request will be pushed there. But when I tried this approach, it really didn't work. The application crashed. I thought, yeah, it's reasonable because you cannot just simply take Ruby attached somewhere and say that it just work, because software development should be more painful than this. But actually it was caused by one limitation of MRI, that MRI allows to have only one native thread per Ruby application. So you may have lots of green threads which we spawn like thread new in our code, but we can have only one native thread per application. But there is a way to avoid this limitation using native extension. This function with this long name RB thread call without GVL, it allows to release global interpreter lock for current thread. It means that you can spawn another native thread and ask MRI to forget about that thread. So it may look like this. We spawn several handlers, which are native threads, and release global interpreter lock for those threads. And now we have Ruby world on one side and Rust world with its own threads on other side. And this approach didn't work too, because of another limitation in MRI, that any Ruby object and any Ruby function and anything in the Ruby world on the left side can be accessed only from the main thread of application, only from the Ruby world. It's because the virtual machine of MRI itself is not thread safe. For example, this is one of the reasons why we still don't have a native thread in MRI. Because let's say if we want to spawn 5 native threads, which will generate 5 random numbers and push them to some array. Array itself is a Ruby object, and it means that as soon as any of the native threads will touch that array, the program will crash. But I really hope that the things will improve in the upcoming Ruby 3 with their new threading model. So we'll see how it will work in the future. And to solve this problem, there may be a need for an intermediate instance. Let's call it core of the application, which will just receive requests from handlers and pass them to Rails. But since there is still a need for a way to transform Rust requests from handlers to Ruby requests, to hashes, it means that it is an interaction with Ruby world. The core cannot be touched still from native threads, from those handlers. But Rust has a concept of channels. You may know them from other languages. Channels are entities which can be shared between threads. For example, in this case, one end of the channel may be connected to core and another to native threads. And channels allow to just pass data without calling any code. So core listens through the channel to handler for request, and handlers push data through the channel without calling any code in the Ruby world. And also core should have some kind of lock to not allow to push more requests while Rails is busy. Oh, can you hear? I think. Okay. 1 2 1 2. Oh, thank you. And can you hear? Thanks. So yeah, core shouldn't allow to push many requests while Rails is busy. It should lock itself if it passed one request. Other handlers should wait until Rails is free. It may be a simple mutex or semaphore, and I will show you a simple scheme how it may work. For example, there is an incoming request on the socket, and first handler fetches this request and tries to pass it to core. Core is not busy now, it's a green state in a locked state, and it may get the request from handler, create a Ruby request object, the rec hash, and pass it to Rails. And when second request comes, core is locked, and second handler cannot push the request to it. So it should wait until Rails finishes its work on the first request, and when core received the first response, it may pass to handler, unlock itself, and second handler may now acquire the core, lock it, and pass to Rails. And the same when Rails finishes the second request, it will pass it back to core, and core will pass through the handler to the client. Now server supports also multi-threaded mode, similarly to like Puma or Passenger, one instance in multi-threaded mode. I will not stop on this mode because it's really a lot of things were happening there, lots of crashes, some threads didn't work, and it can be extracted to a separate presentation, like how not, if you want to write your own virtual machine of Ruby, how you shouldn't do it. Because it's not very human friendly if you try to have like Rust threads, native threads, and Ruby threads. I can show you just a simple scheme in how it grows. So there are more channels which had to be used there, more threads, and if you really want to check out how it works, you can try it on GitHub. This is the repository of the project. The server got a code name trusted for now. It's the same like Rust, trust. You can use it through Ruby gems. I wouldn't recommend trying it for some critical apps like debit credit card processing. I cannot guarantee that you will not lose any data or any money. And I had a question, why it's so complicated to use native threading? Why applications crash? Why cannot be it easier for developers? And I saw one quote on the internet. I don't consider myself as a threading guy. It was said by Mats. Another tweet about that, it was Mats is not a threading guy, so we are not a threading guy. Of course, it's a joke, and I really hope that Ruby 3 still will fix many of these problems. As for benchmarks of the server, I made it in a standalone application without any web servers like Nginx, just simply app server listening on TCP port. You can find the application which was used for benchmarks in this GitHub repository. In single-threaded mode, there was a simple Rails action which renders current UTC time, so without much overhead on the Rails side. The benchmarks look like that. I'm now working to make more benchmarks in different operating systems, but this is on the left on the left side. There is on the right side, right? Sorry. Sorry? Yeah, just Rails action which renders current UTC time. Yeah. Just plain one line of code. This is throughput, how many requests servers could handle per second. For multi-threaded mode, it was a similar action which renders current UTC time, but also it has 100 milliseconds of I/O, just simulating to allow Ruby to switch its green threads. I couldn't benchmark passenger here because I didn't have enterprise mode, but I will do it, and I will add this benchmark for passenger because it's really interesting how passenger works here. As for production usage, I use it for several of these projects, including this blog which I mentioned before. And it works for now, as now I'm more concentrated not on Ruru but on the server, on Trusted itself, and I don't have much to post each week on the blog. So last time I didn't update it for about a month, so server wasn't restarted for a month. It didn't crash itself. I haven't noticed significant memory leaks. So if you can try it for some of pet projects, and if you have some problems or questions, I will be happy to get some GitHub issue. And about the future of the server, yeah, there is like still a lot of work to make there, because this is just small proof of concept. Multi-processed mode, signal handling, also some Rails 5 applications crash. I haven't had time to figure out why. Rails 5 supposed to be still rack compatible, but something was changed under the hood. And WebSockets, more optimizations, and I'm thinking about maybe Windows support, but I'm not sure that it's worth the effort. So thank you for listening, and maybe you have some questions.
Do you have any questions? If so, then I'll bring the mic. Okay.
Did you try to run large application using this server? Like, did it work or not? Because sometimes you just have problems with gems and so on.
It worked because simply, except Rails 5, some of the application, but this application server shouldn't interact with any external gems except Rack itself, because it's an entry point of the application, and most of the things which happen in our Rails app, they happen after that. So we can think about app server as the first middleware in our app. So it worked, and I hope it will work for other apps. We will see.
Okay, no more questions.
Do we have any other questions? Okay.
Tons of questions, actually, but to start, you told us about the how, but you did not tell us about the why. Why did you decide to re-implement what's essentially passenger in Rust?
It was an experiment. I decided to try because, Ruby itself is not as fast as we wanted our software to be, and I decided just to try if I can speed it up or no. That was one of the reasons, just to maybe reduce the time of request response. Maybe if it works, it will allow to reduce our infrastructure costs, because if we can handle the same amount of requests with less amount of app servers, we can save some resources, some servers which we have.
So you benchmarked before, but because when you showed us the benchmarks there, you landed roughly in the same ballpark as Puma and Passenger already. So not much gain in performance, I think.
You mean this slide, yeah?
Yeah, this one.
Yeah, but it means that if it could work the same way for your production application, yeah, and if you are using, for example, Unicorn, it's about 15% of more throughput, meaning that in theory, yeah, if it could work as good as Unicorn, you could reduce 15% of your resources which are used for app servers. And if your application should handle thousands of requests per second, it may be some significant amount of money. Thank you.
Do we have any more questions? I have a very quick one. Could you show the priority queue slide with the results, if you have it? Yeah. Does it mean that the priority is actually computed upon the push? Is it that's why it's so much slower?
I believe in algorithm jam. Yeah, it should be computed on when it's pushed.
Because the popping is like similar.
Yes.
Ballpark. This is like 3 orders of magnitude slower. Okay, perfect.
Thank you.
Thanks so much. Once again, thank you, Dmitry.
Thank you, guys. In the end, I will just say that make experiments, share them, and thank you for listening.
Excellent. Thank you.